Oh. So, I'm going to get started. Wednesday, the 5th, is exam number 2 on chapters 7 through 9. You get one sheet of notes to use as a formula sheet. You can use both sides. You'll need a calculator, not a phone. I will have calculators you can borrow. Much like the previous exam, it's going to be, well, in this case, it's 9 problems, adding up to 100 points. A few of them are multiple parts. And it will be, the whole length of class. And show your work, and you get partial credit if you show your work. Okay. So let's start the review for the exam. These slides are up on Blackboard. I put them up. I updated them today, so they're totally up to date with the right, the only change I made was the date, but it is still totally up to date. So let's start with a summary of chapter 7. So chapter 7 is about work and energy. So for example, a force is constant and parallel to displacement. Work is force times distance. The general formula for work is force times distance times the cosine of the angle between them. The total work is the work done by the net force. So total work is the total force times distance times cosine theta. The unit of work is the joule, and total work is equal to change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared, because kinetic energy is 1/2 mv squared. Work done against a spring force, specifically against a spring force, is 1/2 kx squared. That's the work applied to the spring, not the work done by the spring. And power is the rate at which work is done. So it's work over time. And the unit of power, the SI unit of power is the watt. And because this is work over time, this is equal to force times distance over time. So force times velocity. So I don't think you need that. So work is force dot distance, or FD cosine theta. Work is the change in kinetic energy, is 1/2 mv final squared minus 1/2 mv initial squared. Kinetic energy is 1/2 mv squared. Work against a spring is 1/2 kx squared. Power is work over time. So here, if you have 30 newtons of force that acts along a distance of 3.5 meters, how much work is done? is fairly straightforward. Work is force times distance times the cosine of angle. Here, it's implied that the force and the distance are in the same direction. So cosine of 0 degrees, 30 newtons times 3.5 meters is 105 joules. Any questions? Here we have a 1 kilogram toy car initially moving at 2.5 meters per second, comes to a stop in 4 meters when a constant force is applied opposing the motion. What is the magnitude of the force? So here, work is change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. So that's 1/2 times 1 kilogram times 0 meters per second squared minus 1/2 times 1 kilogram times 2.5 meters per second squared. So the work is going to be minus 3.125 joules. Work is force times density times cosine of theta. Theta is going to be 180 degrees because it's opposing the motion. The force equals work over d cosine theta. So 3.125 joules over 4 meters times the cosine of 180 degrees gives you a force of 0.78125 or 0.781 rounded to 3 significant figures. Here, a mass has a force of 1,200 newtons in the plus x direction, applied for 14.4 seconds, covering a distance of 1.2 meters in the plus x direction. What power is used here? Power is work over time. Work is force times distance times cosine theta. And force times distance times cosine theta over time. 1200 newtons times 1.2 meters divided by cosine of 0 degrees. That comes out to 100 watts. 1200 times 1.2 is 1440 divided by 14.4 seconds gives us 100 watts. That was chapter 7. Any questions about chapter 7? No? Okay. Let's talk about chapter 8. So chapter 8 introduces the idea of conservative forces. Conservative forces are forces that conserve mechanical energy. Non-conservative forces convert mechanical energy into other forms. So conservative forces are things like springs, gravity. Non-conservative forces are things like friction. A conservative force does 0 work on any closed path. The work done by a conservative force is independent of the path. So some examples of conservative forces are gravity or springs. The work done by a non-conservative force on a closed path is not 0 and does depend on the path. Non-conservative forces are things like friction, air resistance, tension. Energy in the form of potential energy can be converted to kinetic or other forms. So there's potential energy, U. Marker. So U of G for gravity is mgh. U of a spring, and this is the potential energy of the spring itself, is 1/2 kx squared. So the potential energy you store in a spring is equal to the work you do against a spring. That's why they have the same formula. And energy is conserved if you're only working with conservative forces. The mechanical energy, E, so E final equals E initial. That's U final plus K final equals U initial plus K initial. That's conservation of energy. So this is conservative. And if you have non-conservative forces, E final equals E initial plus work non-conservative. So U final plus K final equals U initial plus K initial plus work non-conservative. And so the work done by non-conservative forces equals the change in the system's mechanical energy. And potential energy curve is potential energy versus position. So U for gravity is mgh or mgy. Match this book. U for a spring is 1/2 kx squared. Kinetic energy is still 1/2 mv squared. Energy is conserved. E initial equals E final. If all forces are conservative, U initial plus K initial equals U final plus K final. There are non-conservative forces, U initial plus K initial, plus work non-conservative equals U final plus K final. I wrote these. In slightly opposite order on the board. But all I did is just write the equation side on the opposite side. Switch left and right. Any questions about this? Generally look for conservation. So if you have a 12 kilogram stud that starts at rest on top of a 10-meter high frictionless hill after it slides to the bottom of the hill, what is its speed? So this is a conservation of energy problem. So potential energy initial is MGH. Oops, I'm hitting the wrong button. So that's 12 kilograms times 9.8 meters per second squared times 10 meters, which is 1,176 joules. Kinetic energy initial is 0 because it's not moving, because it's at rest. At the bottom of the hill, potential energy final is 0, and we can figure out kinetic energy final. So potential energy initial plus 0 equals 0 plus kinetic energy final. The kinetic energy final is 1176 joules, which is equal to 1/2 mv final squared. So V final is square root of 2 times kinetic energy final over mass. So 2 times 1176 joules over 12 kilograms gives us 14 meters per second. So how much potential energy is stored in a spring with a spring constant of 1,000 newtons per meter that is compressed a distance of 5 centimeters? So do we note that the spring constant is in meters? In general, you want to be in meters when doing these calculations, so you will need to convert the units. So potential energy of spring is 1/2 kx squared. So potential energy of spring is 1/2 times 1,000 newtons. Or this spring is 1/2 times 1,000 newtons per meter times 0.05 meters. That's 5 centimeters squared, which comes out to 1.25 joules. So that was chapters 7 and 8. Any questions about chapters 7 and 8? Let's talk about chapter 9. I'm going to have to erase some of the stuff from chapter 7 and 8. Linear momentum. Oh. P is mass times velocity. It is a vector. We can use momentum to re-express Newton's second law as the sum of all the forces equals change in momentum over change in time. Or with calculus, the momentum dt. Impulse is force times time. It's the average force times time, and it is change in momentum. Impulse is a vector. The impulse is equal to the change in momentum. If the time is short, the force can be quite large. If the net external force is 0, momentum is conserved. The internal forces within a system will always sum to 0. In a collision, we can assume external forces can be ignored. And an inelastic collision is one in which kinetic energy is not conserved. A completely inelastic collision is one in which the objects stick together afterwards. For a completely inelastic collision between two objects, you have mass 1, velocity 1, initial, plus mass 2, velocity 2, initial, equals, so this is 3, equals mass 1 plus mass 2 times 5. A one-dimensional collision takes place along a line. In 2 dimensions, conservation momentum is applied separately to each. In an elastic collision, kinetic energy is conserved. If it's in 1D and one object starts at rest, the solution is V1 final equals mass 1 minus mass 2 over mass 1 plus mass 2 V naught V2 final. Um, 2 M1 over M1 plus M2. And center of mass, the sum of mass times position over the sum of all mass, total mass. And you can do that for y, velocity, and acceleration. So y center of mass is n. Now velocity center of mass is mass. Mass and acceleration of mass. The motion of the center of mass has the property that the total mass times the acceleration of the center of mass equals the net external force. And lastly, for rocket propulsion, thrust is equal to change in mass over change in time and velocity of the expelled material. So the rate at which material is being thrown out the back times the speed at which the material is being thrown out the back. Any questions about any of that? So momentum equals mass times velocity. Net force is momentum or change in momentum over change in time. Impulse is force times time, which is change in momentum. Momentum is conserved if there are no external forces, so sum of all initial momentums equals sum of all final momentums. Elastic collision in 1D with objects starting at rest, V1 final equals M1 minus M2 over M1 plus M2 times V naught. V2 final is 2M1 over M1 plus M2 times V naught. X center of mass is sum of all mx over m, v center of mass, and a center of mass, and plus is rate of material going out the back times the exhaust velocity. So if you have a 3 kilogram mass moving at 4 meters per second, and it hits a 9 kilogram mass at rest, and the two stick together, what is the final speed of the two masses? So this is a completely inelastic collision. They stick together, so their final velocity will be the same. So you can just do this with conservation of momentum. So momentum is conserved. So momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. So that's mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial equals mass 1 times velocity 1 final plus mass 2 times velocity 2 final. But these two masses stuck together. So V1 final and V2 final are the same number. So mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial equals mass 1 plus mass 2 times V final. V1 final and V2 final equal V final. So if we solve for V final, mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial over mass 1 plus mass. So 3 kilograms times 4 meters per second plus 9 kilograms times 0 meters per second over 3 plus 9. So that's 3 times 4, that's 12 plus 0 over 12. It gives you 1 meter per second. Final velocity. Here we have a 3 kilogram mass moving at 4 meters per second. It's a 9 kilogram mass at rest, and the two collided elastically. So what is the final velocity of each mass? So with one mass moving and the other mass at rest, V1 final is going to be mass 1 minus mass 2 over mass 1 plus mass 2 times V1 initial. So 3 kilograms minus 9 kilograms over 3 kilograms plus 9 kilograms times 4 meters per second. That's minus 6 kilograms over 12 kilograms times 4 meters per second. So that's minus a half minus 2 meters per second. V2 final is going to be 2 times M1 over M1 plus M2. times V1 initial, 2 times 3 kilograms over 3 kilograms plus 9 kilograms times 4 meters per second, 6 kilograms over 12 kilograms times 4 meters per second. That is plus a half times 4 meters per second, so 2 meters per second in the positive direction. And then here we have an object made of 3 things, with its center at the origin. Y is up, X is to the right. 1 kilogram here, 2 kilograms here, 2 kilograms here. Where is the center of mass in X and Y? Okay, so to find the center of mass, well, X center of mass is going to be the sum of mass times position for each object divided by the sum of all the masses. So mass 1 times x1 plus mass 2 times x2 plus mass 3 times x3, all divided by mass 1 plus mass 2 plus mass 3. So that'll be 1 kilogram times 0 meters plus 2 kilograms times 2 meters plus 2 kilograms times 0 meters. I'm making this object 1, 2, 3. Divided by 1 kilogram plus 2 kilograms plus 2 kilograms. So that's 4 kilogram meters divided by 5 kilograms, which is 0.8 meters. Then Y center of mass is going to be mass 1 times y1 plus mass 2 times y2 plus mass 3 times y3 over mass 1 plus mass 2 plus mass 3. So that's 1 kilogram times 0 meters plus 2 kilograms times 0 meters plus 2 kilograms times minus 1 meter over 1 kilogram plus 2 kilograms plus 2 kilograms. So that's minus 2 kilogram meters over 5 kilograms, which is minus 0.4 meters. So this will be at 0.8 minus 0.4, about there-ish. Any questions? Well, that is the review. So remember, test will be on Wednesday. You get one sheet of notes to use as a formula sheet. Calculator will be required. Can't use a phone. And there's partial credit. Make sure you show your work. Well, have a nice day. Let me see. Oh. And I will stop very